Hi students, welcome back from break. Hope you had a restful break and are ready to jump into some chemistry. But actually, we're not jumping into anything new. We're going to pause a little bit and just review what we did before break when we set a foundation with Kelvin scale and Dalton's law. So we're going to talk briefly about Dalton's law. You have a notes page for Dalton's law to look at. It looks something like this, okay? And this, before I get started, this is Dalton's law of partial pressures is the big title. Often we just call it Dalton's law. Don't let the name fool you, same thing, okay? And I want to point out we call it a law because it is past the theory stage. This is not just a theory. All experiments that have ever been done in testing this have proved that this still works. So it is a law of nature, not just a theory. It seems always nature works this way, which is really cool because it's a super easy law. There's some not easy laws, but this is an easy law. Dalton's law of partial pressures, which and it is the same John Dalton who gave us the atomic theory way back in the fall. It says, and improved with experiments, I can take these individual parts of a gas and I can add them up and that's all I do to get the total. And I know that seems easy and it is easy, but nature did not have to work that way. Nature could have been like, oh, you put these two together and nothing changes. Or nature could have been like, oh, you put these two together and it quadruples. But all it does is you just put them together and it adds up. So what's adding up to being the pressure of the air that I'm feeling right now? Because believe it or not, there's air all around us putting pressure on us. It's almost 15 pounds per square inch. Okay, imagine a 1 square inch spot on my forehead and a 15-pound barbell. Like that's what it feels like on that square inch. And that's just 1 square inch. I mean, think of how many square inches are all over your body. So why don't we feel it? Well, we're totally used to it. That's why we don't notice it. Okay, but what does this pressure come from? Well, it's from pressure of the nitrogen and the oxygen and the carbon dioxide and the argon and the water vapor and all that in the air adds up together to one big giant pressure pushing down on us all the time that we don't notice because we're totally used to. And that's exactly what Dalton's law says. So check it out. Like in this picture, I have these little needles showing there's this much oxygen and there's quite a bit of nitrogen and a little tiny itty bitty amount of argon. And if I were to add all these up, if you want to take the time to look it up and count the little lines on the dials, you should see that adding these 5 up equals the grand total. Okay, so that's Dalton's law. I can add up the individual parts, the partial pressures, that's what we call those individual parts. And when I add them all up together, I get the total pressure. Now, often in chemistry, that's not super helpful to us because we're going to do it in reverse. But let me get to another example, okay? So I'm checking my car tires and I have my car tire wheel and I test it with the pressure gauge and it says it only has 18 PSIs. And when I open my driver's side door and I look in the opening with a sticker, there's almost always a sticker there that tells you how many PSIs your tire should be inflated to. It says I need 32. So I'm going to take the tank of air, compressed air that I have in my garage, and I'm going to add to my tires. Okay. Well, I take my tire was 18. If I add 14 PSIs from the tank into my tire, what's the pressure of my tire? Well, Dalton's law says it adds together. All right. So it's additive. So I'm going back up now. Here's our equation. The total pressure is the sum of the individual pressures. We often call those partial pressures. Okay. Don't let the vocabulary fool you. And I do want to point out that we often are going to measure pressures in things like atmospheres, millimeters of mercury, or torr. Those are very common pressure units. I gave you 6 in the annotation reading. You don't have to memorize any of those. You just have to recognize. If I say ATMs, you should be thinking pressure. If you can do that, great. So we're going to add up all these individual partial pressures, get a total, or often what is the case is I'm actually going in reverse. Here's what I really do when I'm sitting in my driveway wanting to inflate my tires. I go, hey, look, my tire is 18 PSIs, but the sticker says I want 32 PSIs in it. Gee, I wonder how many PSIs do I need to add into the tire? Okay, so well, if my total is 32 and I already have 18, could we not subtract to find how many PSIs to add from the tank? Yeah, of course we could. It works out beautifully. So Dalton's law says we can add up a bunch of little pressures to get a total, or if I know the total, which is often something we can measure, and I subtract all enough pieces, I can find one missing piece. And that would work great too. So if you flip your notes page over to the back, you've got 3 problems to work. And this is a very common problem that we have in chemistry. And we've done this. We were in the lab. We put the zinc into the hydrochloric acid. It made bubbles. It came out through a tube. You caught it in a test tube. You held it upside down. Remember, I reminded you to hold it upside down before you stick the flaming splint in and went whoosh. Okay, right? So I have a total pressure. Inside my collection container, inside the test tube, if you will, the pressure is 825 total. Now, I did not mention at the time because it wasn't really all that important at the time, but if I wanted to measure the gas trapped in my test tube, I'd also have to be careful because some of the water evaporated as the bubbles were going up inside the test tube. So what if I want just the pressure or the partial pressure of the gas? Well, if I know the total, and I know the little piece that the water that evaporated, the water vapor is, I take the total, I subtract that little piece, and then that's the partial pressure of the gas. So Dalton's law works great both directions. Add up the little pieces to get a total, or take the total, subtract all your little pieces, and find the missing piece. Of course, it has to be just one missing piece that's missing, but it's super handy in that regard. Okay, here's, you have practice problem 2 here to fill in. This one is, I'm just combining. Here's oxygen. It has a pressure of certain millimeters of mercury. Here's some nitrogen. It has some millimeters of mercury pressure, and I just want to add them up. Okay, so there we go. Just add it up. Put your answer in that little box there. And then third problem, notice what I have here already. It's telling me I have a total pressure. So 4 ATMs, 4 atmospheres, is the total. If gas A is 1 atmosphere, then how much was gas B in order that they add up to 4 atmospheres? Okay, so you put your answer in the box there, and that's it for the practice, okay? So again, Kelvin's law and Dalton's law, super easy, but foundational. Like, we will use these a lot in the coming days as we go through the rest of the gas law. So I want to be sure that you had a chance to review and master them. Hope this was a review video and not something brand new to you. If this feels brand new, maybe go back and watch it all over again one more time to be certain you got it straight in your head, and you can do these kind of problems with relative speed and ease. Good luck on the practice. Again, these 3 problems on the back of the page are your practice. Once you've got them filled in, turn them in, and good luck.